Okay guys, this will be the last video for the chapter 11 on solutions and colloids. So this video will discuss the colloids briefly. We're just going to talk about what the colloids are, and we'll list several examples of them using different figures. So this slide has the definitions. We've been talking about solutions, which are homogeneous, and the key feature is that the components are mixed together uniformly at the molecular level. As a consequence of this, solutions are typically transparent, and they're also thermodynamically stable. That is they don't fall apart on their own. Suspensions, on the other hand, would be examples of heterogeneous mixtures, and they appear cloudy, and sometimes they can be completely opaque. And the suspended particles in the mixture are typically very large and therefore not mixed at the molecular level. And as a consequence of this, they will eventually settle out. And so here's some examples. So suppose that you've got an aquarium, and it's got, of course, like let's say it's a saltwater aquarium, and you've got all sorts of minerals dissolved in it. So here, the solute is small. The ions are small, and they're uniformly distributed throughout the solvent. In something like mud water, okay, you've got big particles of dirt that are suspended in the water, but they're very large, and eventually they will settle out of the solvent, and they'll deposit at the bottom of the solution, and you'll have water up above. Well, you can have solute particles that are in between these two extremes. So bigger than ions, individual ions, but much smaller than large chunks of dirt. So something in between, and this would and milk would be an example. So the milk fat within the milk would be in between sized particles between these two extremes. And these types of mixtures are called colloids, or colloidal dispersions. And so there you have large particles that are dissolved, but unlike the suspensions, they're not so large that they will have to settle out. So the colloids can be very stable. They also exhibit what's referred to as the Tyndall effect, which allows the colloidal mixture to scatter light. So for example, if you shine light through a solution, a homogeneous solution, the light will just pass right through. But for the colloids, the particles are so large that they cause the light to bounce off in different directions. And so as a consequence of the Tyndall effect, the colloids may appear to be cloudy and opaque as well. Like milk is opaque. Here's an example of the Tyndall effect where you have some colloidal mixture in the gas phase. This could be smoke, or it could be some aerosol, something like that, where you have the light passing through the colloid, and you see the light beam. So that's an example of light scattering off of the colloidal particles, going in different directions so that you can observe the beam of light. Just some terms about the dispersions. So the dispersed phase of a dispersion are the particles that are present in the smaller amount. And the dispersion medium, it's the equivalent of the solvent. It's the substance or solution through which the particles are dissolved. And this is a cute table. It lists different types of phases that are combined as the dispersed phase versus the dispersed medium. So solids dispersed in a gas would be something like smoke or dust moving through the air, versus having a solid dispersed in a liquid. So this would be things like inks and paints. You can make them out of starch and water. This type of colloid has a name called a sol. You could also have solid phase dispersed in another solid phase, so some types of gemstones fit that, some types of alloys, no special name there that I'm aware of. You can also have a liquid dissolved or dispersed throughout a gas. So these are things like clouds and mist and sprays. We call those aerosols. Liquid dispersed through another liquid. Milk, butter, mayonnaise. These are called emulsions. Liquids dispersed through solids are called gels. If you disperse a gas through a liquid, it's called foam. You can also disperse gas through a solid, pumice stone, I guess, different types of floating soaps. Anyway, all sorts of possibilities here for colloidal dispersions. How are they prepared? Well, one way is the so-called dispersion method, where you take large particles and grind them up into smaller particles that would be appropriate for making the colloid. You can grind them up. So, for example, grinding up paint pigments for a certain amount of time to get them to just the right size so that you can make the paint. The other approach would be the bottom-up approach, where you build the colloidal particles from smaller units. So, for example, like a cloud, it grows from a water droplet that's in the atmosphere. Building up the colloidal particles from smaller particles is the condensation approach. Different types of colloids can form spontaneously, but this is just because the particles already have the right size. So things like the foods like gelatin, so when you make jello, or if you powdered milk, if you rehydrate the powdered milk is already the right size to form a colloid. And then the emulsion method here for preparing liquid colloids, two immiscible liquids are shaken together, and then the dispersion is stabilized by using what's called an emulsifying agent. So an agent that allows the two otherwise immiscible liquids to mix together. And so kerosene and water, for example, are two immiscible liquids. However, if you use some soap in that mixture and shake it up, you can get the kerosene and the water to form a stable emulsion. Milk is an example where the butterfat normally would not want to be dissolved in the water. However, the presence of a protein called casein, which acts as an emulsifying agent, allows the butterfat to be dispersed throughout the water. Mayonnaise is another example. Oil and vinegar don't mix, but if you use some egg yolk and shake them up, you can make mayonnaise from that. I'm sure it's more complicated than I've alluded to, but that's the basic idea. Another topic that's important in this to this idea of emulsions, soaps and detergents. Okay, so soaps are hugely important in our world. Obviously you need to wash your hands now more than ever, right? Soaps and detergents are pretty cool. They're these amphiphilic molecules that have both a nonpolar or hydrophobic end and a polar end, a hydrophilic end. And so here, soaps are salts of fatty acids. So here's the fatty nonpolar hydrocarbon chain of a very common soap. Okay, it's a long hydrocarbon chain, and then the carboxylic group here on this side is charged. Okay, and so this end of the molecule is water-loving, hydrophilic, and then the nonpolar part is water-fearing or hydrophilic. Hydrophobic. Hydrophobic on this end, hydrophilic on this end. So this end contains a polar group. This long end here is nonpolar. Synthetic soaps, so detergents, they're very similar in structure. It's just that they contain a different head group. Okay, so a sulfate or a sulfonate head group. How do they work? Well, what happens when you take the soap and you dissolve it in water. So, and then you lather up the soap. What happens is the soap molecules, they arrange themselves in a little ball where you've got the water-loving groups on the outside and the hydrophobic groups on the inside. Okay, and so it forms a little sphere here, and you're looking at a cutaway of the sphere. And so those long hydrocarbon tails are all entangled with one another here in the center of this so-called micelle, as it's called. And so what happens is that like let's suppose you're trying to get some grease off your hands. You lather up the soap, and what happens is the grease is a nonpolar molecule. The grease will be attracted to the inside of the micelle, and the water will stay on the outside of the micelle. And so what can then happen is then you can rinse the micelles off your hands with the grease encapsulated inside the inside of or in the interior of the micelle, which is pretty neat and useful. So soaps and detergents are pretty cool chemicals. Another property of colloidal particles is that they can be charged, and therefore they can be manipulated with electronics and electric fields and such. The fact that, for example, iron 3 hydroxide colloids, which can be built, are positively charged, helps to keep them from aggregating together, right? If they weren't charged, they might coalesce and then form a precipitate and fall out of the suspension. But if they're charged, if the colloidal particles are charged somewhat, then they are less likely to coagulate or aggregate. Another useful aspect of having charged colloidal particles, for example, smoke particles, are often charged, and so that provides with the strategy for removing pollutants from air. So, for example, if you have soot-laden smoke, so the dirty smoke comes in, the particles are charged, you can use electrodes inside this device here to attract those charged particles, which will then, fall down as, they'll grow in size and they'll eventually fall down here, and you can remove the soot, and then the soot-free gases can escape. Now, these may still be pollutants, but at least you've pulled out the dirty soot from the polluted air. Finally, this last slide is just on gels. Recall that the gel is when you have some liquid phase dispersed throughout a solid medium. It's a very viscous type of colloid. The reason I include it is because Jello is an example. So you have this gelatin protein, so this large molecule that forms a solid, and then the Jello is made by dispersing a sugar solution throughout the solid material, and so that's what gives, and food coloring. So that's what gives the Jello its shape. The Jello is essentially the gelatin, and then the flavoring and the coloring comes from the sugar solutions that's dispersed through it. Jelly is another example of a gel where you have sugar and sugar solution dispersed throughout a carbohydrate called pectin. Silica gel is another example. In that case, you have a hydrated silicon dioxide. And so those are the colloids. And so I'm going to stop this video here, and we'll start the next one with the next chapter on chemical kinetics.